Lesson 4 is going to be ionic equations. These are really important. You're going to have, we have to understand kind of a little bit better about what's actually taking place in these solutions. We've talked about this before, but we're actually going to write out some equations based on that today. And also, I'll tell you right now, you will get at least 3 questions on your Unit 4 test on this, and you'll get probably at least 3 questions on your final exam. So the thing is it's kind of important stuff, okay? And it's important because it basically is what's happening when you look at single and double replacement reactions, okay? So when we talk about ionic, mixing 2 ionic compounds together for that matter, we're not talking about 2 ionic compounds that are being mixed together. We're talking about the ions that we're mixing together, okay? And we'll talk a little bit about this as we move on here today. For example, this one right here, okay? This is your first example kind of thing that I did for you. We're going to do some of these together today. But when you take sodium chloride, okay, a sodium chloride solution. So yesterday we had, for example, some sodium hydroxide, we had some copper 2 chloride, we had some pretty red stuff, cobalt 3 chloride, or 2, cobalt 2 I think, chloride, okay? When you take those solutions, what's actually in them? It's not solids. You didn't see solid. There was one that didn't really dissolve that well, so just forget about that one. But if you think about the sodium hydroxide or the copper 2 chloride or the cobalt 1, did you see any solids in those solutions when you started? No. Why? Because they're ionic compounds, and when you place them into water, they dissociate. Unit 3, yes? Dissociation. So when you put sodium chloride into water, you get sodium ions and chloride ions, correct? So in that beaker, when you took the little pipette that we did yesterday, the little squeezy, or what do you call them, dropper, when you take the dropper, okay, and you take that solution out and you put it in your test tube, you're actually taking sodium ions and chloride ions. That's what's actually in that solution. You took no solid, right? There was no solid to take out. There was a chunk of solid. That's different. That was a metal by itself. But as far as sodium chloride or copper 2 chloride or cobalt 2 chloride or whatever the other ones were, there was no solids there, okay? If you put silver nitrate into water, you get silver and nitrate ions, dissociation. When you mix all those together, remember, positives, negatives. Positives are attracted to negatives. So are these still 2 attracted to each other? Sure they are. But remember, sodium chloride is very soluble. So do they stay together? No, they break apart, dissociate, okay? Silver ions and nitrate ions come together. Their opposites attract. Do they stay together? No, we already said that it was aqueous. They break apart. They're individual ions. Is sodium attracted to nitrate? Opposites attract, yes. Very soluble, though, when you look it up, so they break apart. One more here. Is silver attracted to chloride? Yes. Opposites attract. They come together, but they stay together. That's the precipitate that's formed. Yes? Yeah.
Why can't Na
They do, but they're very soluble. So they come together, and there might be a couple that stay together, but for the most part, water's strong enough to break them apart. Right? Just like when we started up here, when you take sodium chloride and you put it into water, it is a solid initially. Put it into water, breaks apart into sodium ions and chloride ions. Are those 2 attracted to each other again? Absolutely. But when they come together, water's strong enough to pull them apart again. Okay? So they absolutely are. Just like silver and nitrate are still attracted to each other, but once again, water's able to pull them apart. Now, do you have, like, once again, do you have some silver nitrate as a solid in there? Probably. Yeah, there's probably a couple molecules that have joined together, but you probably not enough for you to see. Okay? Solubility is usually pretty good with those. All right? So that's how you get this precipitate here. This is what we call the molecular equation, and the molecular equation here is not because it's molecular compounds. Look at those. Those are not molecular. Those are ionic. We're doing double replacement reactions, ionic compounds. The reason it's called molecular is because it's what happens on a molecule level, okay? On a molecule level. Ionic equations make sense. Look at, we're talking about ionically, ions that are involved. What's actually happening there? Opposites are attracting each other, right? Et cetera, et cetera. And then there's one more that we need to do, which is called the net ionic equation, which is, we'll do that later here, okay? The 3 questions you will get from these questions, or from this question on Unit 4 and in the final, I'll tell you right now. I'm going to give you an equation, and you're going to have to write out, one will be, what is the ionic equation for this? That'll be multiple choice, A, B, C, or D. Ionic equation. What is the net ionic equation? A, B, C, or D. And what are the spectator ions, which you don't know yet, which we'll do, okay? I'm telling you right now, those are the 3 questions you're going to get, okay? Guaranteed. And they might be on the same question, they might be on different questions. So I might give you all in the same one here. Probably not. You'll probably get different ones for each one, okay? Well, let's do some. I'll show you. Okay, right now, here's what I need you guys to do for me. You guys are going to start with what we call the molecular equation, or AKA a basic double replacement reaction for sodium hydroxide and magnesium chloride. Keep in mind, if you're going to do it in that space, listen, you're going to have to do 1, 2, 3 equations underneath each other. So if you don't have enough room, if you don't think you have enough room, flip your thing over to the very back, and there's an empty page right there for you, and we're going to do 3 examples today, okay? Up to you, up to you. If you think you can fit them in that space, then fine. If not, then flip to the back, okay? Do the molecular equation, aka a double replacement reaction. We were going to have a quiz today, but I'll tell you what happened with that in a second here, but we don't need to broadcast that. But let me just turn this off here. Where are we? There we go. Okay, quit talking. All right, sodium hydroxide. Sodium hydroxide, 1 plus, 1 minus, of course. Solution, right? You can look that up. It's very soluble solution. Sodium hydroxide and magnesium chloride. Magnesium is a 2 plus, chloride is a 1 minus, so swap and drop, and you'll get that, okay? So we know, of course, when we did double replacement reactions, I said the metals switch places, and you're going to end up with sodium chloride and magnesium hydroxide. How do you know those states? You need to look them up on the back of the solubility chart on the back of your periodic tables. That's how you know them, okay? That is very important, because if you get that wrong, well, first of all, we're going to do other stuff with that, I told you already. Secondly, these equations are going to be wrong based on that one alone, okay? So you have to understand aqueous solid, all right? We need to balance it. So I think I need a 2 here and a 2 here, and I think we're good. And that's what you need to be able to do for one of the questions on your quiz on Monday, okay? Make sure. Ionically, what happens? Okay? So, when you put sodium hydroxide, sodium hydroxide is a solid, okay? Comes in little pellets. And when you put them into water, basically what I did was I grabbed a beaker, I took sodium hydroxide, I dumped some in, okay? I went over to the water, put some water in. When you put sodium hydroxide with water, it dissociates. It breaks up into ions, right? So, what ions do you get? Well, sodium ions, hydroxide ions. Okay, oops, I need a plus in there. I probably should spread that out, sorry. Sodium ions and hydroxide ions in water, okay? We used sodium hydroxide yesterday. So if you remember, if you went up to the sodium hydroxide, you didn't see any solid in there. It looked like a clear solution. It's a base, obviously. Sodium ions and hydroxide ions are what's floating around in that solution, okay? Here. Oh, let's balance this too. Look, 2 sodium hydroxides. I need 2 sodiums, 2 hydroxides, right? 2 NAs, 2 OHs, yes? Okay? So we're just going to make sure that we have the same number on both there. Okay? Look, magnesium chloride is aqueous, very soluble. So when you put it into water, you get magnesium ions and chloride. That's chloride ions. Magnesium ions, chloride ions. Aqueous. Okay? Chloride comes as a 1 minus. Okay? Now, once again, we got to look back up to the top there and make sure we balance it appropriately. Magnesium gives off 2 electrons. Chloride gains 1, so I need 2 of those to make sure that I gain them, right? When you are done with ionic compounds, the charges have to cancel out. They're neutral. Look, 2 plus, right? 2 minus, 0. 2 plus, 2 minus, 0. Okay? Have to. On the other side, I have sodium chloride, and it's also aqueous. So I know I probably have some sodium ions and some chloride ions floating around in this solution. In fact, I'm going to have 2 of each one because I have 2 sodium chlorides. So that basically implies that I'd have 2 sodium ions and 2 chloride ions, based on the top balanced one, of course. So that one also breaks up. So when you look at your test tube from yesterday, right? Test tube, solid, right there. Up here is a clear solution. In this case, it would probably be those 2 things floating around in that solution. You don't see the ions because they're not together. So you see that floating around probably. That's what would be there, okay? So, sodium chloride. And lastly, we have some magnesium hydroxide. But magnesium hydroxide has come together and stayed together, right? It's a solid. It floats to the bottom. You see it. So what we need to do here is rewrite magnesium hydroxide solid. It is an ionic compound that has been formed, and it's a solid form. Comes together. You guys saw this yesterday. Comes together and usually settles to the bottom, right? Yes? Okay. That you can't break up because that one, water's not strong enough to break it apart, right? It's come together. It's insoluble or slightly soluble. So it comes together and it stays together. That's the precipitate. That's the solid. It stays together. Okay? Questions? Yes? Solubility chart. Yeah, that's what you got to go based on. Break apart. Solubility high basically means that when you put it into water, water will pull it apart and it'll stay apart because you'll get individual ions. If it's bottom row solubility, then it's going to come together, but it's going to stay together because what happens is it doesn't break up very well. So when it comes together, it just stays together. You can't break it apart as easily. And that's all based on your solubility chart. Okay? So, is it important to make sure you get the right solid here? Absolutely. Because the next thing you're going to do here is if you look at this equation, you'll notice that you have ions that are the same on both sides. Sodium ions and chloride ions are the same. Look, sodium ions, 2, 2, 2, 2. Same on both sides. Those ions, since they're the same on both sides, are called spectator ions. Those are your spectator ions. Okay? Spectator is what they're called. Because, of course, well, we'll look at the next part here and you'll see why they're called spectator ions. The last part here is called the net ionic equation. Okay, and this is in your notes as well. It's actually on the back of the first page, but don't worry, just look up here for now. You can look that stuff over later. The net ionic equation. These are actually, I call these reactions mini. M-I-N-I, mini. Meet me. Cooper. Okay, never mind. That wasn't funny all day today for some reason. I'm not sure why. Because it kind of is, but okay. The net ionic equation says what's actually happening here. What's the overall thing what's the overall equation that's being involved here? And the sodium and chloride ions are the same on both sides. So basically they're watching the rest of this main tidal event here. So what's left over if I took out the spectator ions? I just wrote that one there and I wrote that one there. And the reason I did, because I like to have the metal first and the non-metal second. So that's the only reason I switched them around there. No biggie, okay? You don't have to. I'd prefer if you did. because the metals always come first and then the non-metals. And then, of course, over here, you get magnesium hydroxide, solid. Okay? Basically, you're looking at that, and that, and that, the blue stuff, right? Right there. Okay? You just basically take out the spectator ions, and you write what's left over. So if you do the first one really well, the first equation, and then from that you can kind of decipher the second one, well, the net ionic equation is easy, because you just take out what's the same on both sides and rewrite it. Okay? All right, I'm going to give you guys a little bit more practice with that, but is there any questions with that one so far? Okay? Questions so far? This is what really is happening in this test tube or this beaker. You're taking magnesium ions and hydroxide ions and you make magnesium hydroxide. And that's the solid that you'll see, of course. Okay? Yep. What do you mean, which one do you choose? Hydroxide? The sodium chloride? Sodium chloride is very soluble on the back of your periodic table. You choose the solid. Yeah. Okay? So, take out the spectator ions, that gives you the net ionic equation. Okay? That's pretty much it. They can get a little bit more tricky just with the balancing part, but the same stuff it's basically the same stuff, and we're going to do a few more examples here. However, okay, let me ask you a few questions then. Is there any, first of all, do you guys have any questions? Okay. Let me ask you a question. So if magnesium and hydroxide come together to form this, why did I do all this? Why did I do the first two anyway? What's the purpose of the first two reactions? Any ideas? Why? I'll ask you this. Why, if this is a spectator ion, sodium ions, and then I get sodium ions over here, why do I have the sodium ions there even then? What's the point of having them there? What's the point of these chlorides if they're here and then they end up over here? What's the point of the chloride ion being there? Answers? Anyone? Well, let me ask you this then, which probably will hopefully answer your question because I've asked you this a few times. Can you go into the back room and get the magnesium ions from a bottle and the hydroxide ions from a bottle and mix the two of those solids together and get magnesium hydroxide? No. What's the purpose of the sodium ion? What's the purpose of the chloride ion? Yep. Kinda. What's the purpose of the sodium ions and chloride ions? Ionic compounds involve what? Metals and nonmetals. What happens with ionic compounds, metal to nonmetal? You do what? Gain and lose electrons. Why is sodium here? Well, because we need to get hydroxide to have a 1 minus. Yes? Where does that extra electron come from? Sodium. Right? If there was no sodium in here, where would that extra electron come from? The answer is, don't know. Magnesium needs a 2+ charge. Where do those electrons go? Magnesium by itself, how am I going to get rid of 2 electrons? And the answer is, you're not. There has to be a nonmetal to take those electrons. So we chose chloride. Could you do this reaction with something different? Yes. That's why they're called spectator ions. They're watching this reaction take place. Could I have used potassium ions here and got the exact same result? Yeah. Because the potassium loses its electron to hydroxide. Magnesium still gives its electrons to chloride. The only thing that changes, of course, is my spectator ions. Now I end up with potassium ions over there, but I would get the exact same net ionic equation. In fact, I could do this reaction for you. Potassium hydroxide with that, and sodium hydroxide with magnesium chloride. I could put them right beside each other, and you wouldn't be able to tell the difference. They look exactly the same. because you can't see the ions floating around in here. Okay? Can't see those. The only thing you're going to see is the solid, and you get the same solid. I could even change this one. That doesn't have to be chloride. It could have been nitrate. Nitrate is very soluble. What do I get on the other side? I get nitrate ions again. Okay? The overall reaction is right here. That's the net ionic equation. So the three questions you are going to get on your test and on the final are going to be, question number 1 would be, here's a list of 4 reactions. What is the ionic equation reaction for example, the top one there, molecular equation. So I'd say sodium hydroxide mixed with magnesium chloride. What's the ionic equation? A, B, C, or D? And you'd want to pick the middle one there. The second one, other question you're going to get is what is the net ionic equation? And of course you'd want to pick that one there. And the third one is going to be what are the spectator ions for this reaction? And of course you'd want to pick, in this case, sodium ions and chloride ions are the spectator ions. Okay? And those are the 3 questions you will get, I guarantee. Okay? There is probably right there, that's 9% of your test right there. 10% maybe, roughly. Easy 10. Okay, here we go, next one. I'm going to get you guys to do number 1 from your homework, so back sheet. Number 1, you guys are going to start that. You're going to write out the molecular equation for sure, and then I want you to start on the ionic one, and in about 2 minutes or 3 minutes or so, I'm going to put the molecular one up. I'm going to do it a little bit behind you guys, but I want you to start with the molecular one, balance it, states, ionic, start that one, and I'll put up the molecular one just to make sure we're on the same track here. Number 1 from this sheet here. It's on the back of your handout. It's been last page of your thing I just gave you today. Okay, so the molecular equation, I need to balance this yet, but once again, calcium chlorate, calcium is 2 plus, chlorate's 1 minus, swap and drop. Sodium's a 1 plus, sulfate's a 2 minus, so swap and drop. Sodium chlorate, 1 plus, 1 minus, and calcium 2 plus, sulfate 2 minus, swap, drop, reduce. So you're going to have to look up the states. So aqueous, that's very soluble, that is slightly soluble. Bottom row, back of the periodic table. Balancing. I got 2 sodiums, 2 chlorates. Let's put a 2 there. You're done. Okay? So that's what you should start with. That's something you need to be able to do for Monday. Yes? Double replacement reaction, balanced states. Ionically, are you guys ready or not yet? Yeah? Calcium chlorate, very soluble, aqueous. When you put that into water, you get calcium chlorate. Calcium's a 2 plus. Chlorate is a 1 minus. Okay? If you're not sure about the ions, just say the words. Calcium comes in a 2 plus. Chlorate is a 1 minus. That's actually all I'm going to do with that one. I got to go back and balance it later, but look. Sodium is a 1 plus, and sulfate is a 2 minus. Okay? Sodium ions, sulfate ions. I'll go back and balance it later. Sodium chlorate. Okay? Sodium chlorate. And then we got calcium sulfate, but calcium sulfate as a solid stays together. So I'm going to write down calcium sulfate solid. Let's go back and balance everything. Make sure. So, calcium's a 2 plus. Okay, look up here. This is balanced up here, this reaction. So 1 calcium, 2 chlorates. I need to put a 2 right there. Okay, maybe I'll do it in a different color here. 2. Okay? Always compare it to the top one. If the top one's good, the next one should be good. Sodium's at 1 plus. I got 2 right here, so I need to have 2 right here. Sulfate, sulfate, good. Okay. 2 sodiums, 2 sodiums, 2 chlorates, 2 chlorates. 1 calcium sulfate, 1 calcium sulfate, we're done. Good? Questions? That's the tough part, if that's tough. Okay? Last part, net ionic equation. What's exactly the same on both sides? Well, let's see. 2 chlorates, 2 chlorates, 2 sodiums, there you go. Okay? Yes, there is a shortcut. Okay? And it might save you some time on the test or something like that if you can see it there. But I'm not going to tell you about it. You'll figure it out. Okay? Net ionic equation, what's overall happening here? Calcium 2 plus, sulfate 2 minus. Remember, we take out the spectator ions and just write what's left, right? So, calcium ions, sulfate ions gives you calcium sulfate solid. 2 plus, 2 minus, swap, drop, and reduce. Okay? And there you go. Good? All right. So, calcium sulfate. Good? Yes? Questions, anyone? Yes, no? Okay. Those were 2 double replacement ones. Okay. We're going to look at a single replacement real quick here. We're only going to get one of those done. We're going to go back to right here, your examples. And we're going to do zinc and iron 3 chlorate. So same thing, I want you guys to write out the single replacement reaction for this, which is something you should be able to do once again for Monday. The single replacement molecular equation, basically the molecule equation. Okay? So go ahead and do that right now. We'll give you a few seconds here. So, single replacement reaction, zinc and iron 3 chlorate. Now remember, when you do single replacement reactions, you're going to have a chunk. We did this yesterday with aluminum, the very first one, aluminum chunk, zinc solid, aluminum solid, and copper 2 chloride solution, obviously. We need to have a solution there, so iron 3 chlorate solution in this case. Metal switch places, we get iron solid and zinc chlorate. Zinc's a 2 plus, chlorate's a 1 minus. Okay? Yesterday, when we went to the lab, okay, you guys did aluminum and copper 2 chloride. And then I said after a while you're going to shake it and see what happens. And you saw a red solid precipitate fall to the bottom, right? So you saw those metals switch places. I'll actually tell you what happens today. Why does that happen? Okay? We need to balance this. So 3 chlorates here, 2 there. So let me do a 2 here, and a 2 here, and a 3 here, and a 3 here. And that is your molecular equation, balanced. That's, once again, something you need to be able to do on Monday. Okay? Single replacement reaction, straightforward. Ionically, what happens? Well, you got 3 zincs here. I'm going to write that 3 zinc solids. What's the charge on this zinc right here, guys? Charge on the zinc right here. Nope. Guess again. What's the charge on this zinc? Huh? 0, because it is not an ionic compound. You get ions, charges, from ionic compounds. This is a metal by itself. That aluminum that you had yesterday and that magnesium strip that you used had no charge on it. That is a solid chunk of just metal. No charge. You have to have a non-metal with it to lose electrons. Okay? No charge. So this is the tricky part. You have to remember, elements by themselves don't have charges. We've talked about this a few times now. Okay? This here is an ionic compound. It's iron 3 chlorate. So it looks like that. And yes, we need to balance it accordingly. So my question to you is, how many iron ions do I have up there? in the top equation? How many irons are there? How many? 2, yes. How many chlorates do I have in the top equation? How many? 6. All right. 2 and 3, right? 6. Yes? Remember, the charges need to balance. 6 plus, 6 minus. I'm not going to do that, though. Let's go 6 minus. Okay? Yes? 6 plus, 6 minus. Ionic compounds neutral when they come together because all the electrons that were lost by the metal are gained by the non-metal. That's how you get charges on stuff. This iron here, what charge goes on that iron now? Charge on the iron. Hurry up. Let's go. Come on. No charge. Zinc. Okay. Zinc is a 2 plus. And I ran out of room here. Chlorate is a 1 minus. And once again, we're going to have to balance those two. How many zincs do you have in the top row? 3. Yes? How many chlorates do you have? 6. Okay? That's the ionic equation. Yes? Net ionic. Well, same as before. To get the net ionic equation, we take out the spectator ions. What's exactly the same on both sides? And the answer is chlorate, 6 and 6. Is zinc the same as zinc 2 plus? No. Is iron the same as iron 3 plus? No. We've got to leave those. But they're not. Zinc chlorate's soluble. Yeah. Only you got to put the ones together that form the precipitate or the solid. Bottom row, yes. But those two are soluble. That's what happens in single replacement reactions, usually. Okay? Net ionic, we take out the spectator ions. In a single replacement reaction, you get 1 spectator ion. In a double replacement reaction, you get 2 spectator ions. Easy to remember. Single 1, double 2. Okay? So we take those out, and your overall reaction, rewriting it just as you see it above here, as always, is this. Okay? There you go. Wrote exactly what I see above there without the spectator ion in it, in this case. Okay? That is your net ionic equation. Okay? Questions, anyone? That's all we're going to have time for the single one today. We'll do another one on Monday. I'm not going to keep that one for homework. Okay? But questions, ask now while it's still fresh, yeah? No, the other ones aren't exactly the same. Zinc's not the same as zinc 2 plus. Difference of electrons there. Don't pack up yet, we're not done. Not done. We still got more writing to do. They're not exactly the same. Okay? Only the chlorate, 1 minus, chlorate, 1 minus is the same, 6 and 6. Now, what happens in a single replacement reaction? Well, look, how does zinc get to be zinc 2 plus? What has to happen? Think about that. How does zinc become zinc 2 plus? It has to do what? Not quite. It's tricky. How does zinc become zinc 2 plus with a 2 plus charge? Yep. Lose 2 electrons. And look, there is 3 of them, yes? So if I just looked at this particular reaction, it'd be a total of 6 electrons, yes? Right? How does iron 3 plus become iron? Iron 3 plus, how does it become back to iron? It has to do what? Gain 3 electrons, right? But there's 2 irons, so times 2. Right? So all the zincs are losing 6 electrons. Those 3 zincs are in total losing 6 electrons. Those 6 electrons are going to the iron. Okay? So what actually happens in a single replacement reaction? Electrons are transferred from one metal to another metal. That's what happens. In Chem 30, you will learn which ones do that very well and which ones don't. Basically what's happening here.
Good afternoon, everyone.
Okay, so we'll learn about that in Chem 30.